This is too funny, this is too funny, this is too funny. Well, at least. Well,
I did my shift. What about you?
at least when I come all this, I don't have to do restrict me, so I can actually see the rest.
Oh my god. It's going to be a good take someone who would turn it on. All right, everybody, I think I'm gonna go ahead and get started here. Welcome to another week. Another episode of General Hospital. No, this is Map 250B. Sorry, it's not a soap opera. I just sometimes teach like it is. I'm hoping this is gonna go well today. I did walk more than 20 miles yesterday, so it could be interesting. I decided to wake up at 4 a.m. and drive to Palm Springs so I could, I don't know, exercise, I guess. I found a trail I wanted to do, and the trail went next to a mountain. So of course I had to climb the mountain too. I'm what they call a peak bagger. If you drive around and you see some high point on the ridge, it's like, I want to go there. Right? I'm always trying to go to the highest place I can find. So I got quite a bit of exercise, and I was not walking very well last night, but I'm doing much better now. But I'm really glad to see you. That's why it took me a little extra time to grade your quizzes. You turned those in on Sunday night. I finally this morning was able to look at those. And I also put, they went really well, by the way. So the quizzes were fine, but I did put a copy of the solutions into the midterm 2 resources folder. So if you want to check out my way of writing up those subspace verifications, or how you check if some vectors are Li or span or both or neither, those were the kind of things I put. I decided to make the quiz exclusively chapter 4. So anyway, if you just want to look at the solutions that I put together for that, feel free to look in Canvas in the midterm resources folder. And I would definitely recommend that you do that if you didn't get full credit on anything. So I scored those, each problem out of 1 point, and I gave either 0, a half, or 1, depending. So if you lost any points at all, it's definitely worth looking at that, because I'm probably going to be asking you similar questions to that when we get around to our midterm. Speaking of which, that is on Thursday. So this Thursday we have a test. Let me just remind you here, midterm 2. And it will cover almost all of chapter 4. So there's 10 sections in chapter 4. We did skip 4.7. So I will say except for 4.7, you don't need to think about that section, but everything else in chapter 4, we did that. I would estimate that this is likely going to be half the midterm, is just the chapter 4 stuff. That's a rough guess. I have not written the test yet, but I'm guessing it's going to come out something close to that. Then we have the 3 sections of chapter 5, which we've done much more recently over the last week or so. And that might be roughly 30% of the test. Again, it's a rough estimate. And then we did cover that first little bit about linear transformations. And that was section 6.1. You've only done 1 homework on it. So probably maximum of 20%. It might even be a little less than that. But that's kind of what you should expect. If you really want to see a nice example, I would just recommend taking a look at the sample midterms. There's 2 of them in the Canvas resources folder for you. Also, in terms of what other ways of looking at this, homeworks 9 through 14 are the relevant homeworks for this exam. There is 1 more due tonight, which is actually number 13. We've already done 14. We're kind of going backwards. So I'm going to take some questions on homework 13 today in class. And those are the homework. And then in terms of group works, they would be group works 6 through 9. Now we've actually only done 6 and 7 so far, but we're going to do both 8 and 9 today in class. So we're actually mostly going to spend today reviewing. I don't normally review for an exam in class because there's already a review session that you can watch. But we're doing great with the material. Again, all these videos you guys have watched and just keeping up to par with everything. We're in great shape. I'm not in any big rush to like move on. I might start talking about another section in chapter 6 today, but it will only be material that I think would be like enhancing and reinforcing the stuff that's already on this list, as just a little bit of extra help with the stuff that you're studying for this exam already. So anyway, so that's what the exam is going to cover. Now, I can also remind you about my extra office hours. I didn't actually put these into the review packet, so you might want to jot these down or take a picture of it after I write these down. Obviously, I have hours tonight, like I always do, Tuesday evening after my second class. I'll be there all evening except for a 1 hour dinner break at about 9 o'clock. I'll be around all night tonight. But in terms of extra hours, I do not normally do Wednesday office hours, but I will do them tomorrow, starting at 10 a.m. Can you believe it? I'll actually get up in the morning for a change. Unlike this morning, which was rough. After walking 20 miles, the next morning is usually a little hard to get up. Anyway, tomorrow I should be fine. So about 10 a.m. I will be both in my office and in Zoom. So if you don't want to come all the way down to campus and just want to ask me something in Zoom, feel free to do that. And then I'm also going to be around in the evening tomorrow night, all evening, basically. So feel free to come by. I have a friend I go to dinner with every Wednesday evening, but I should be back by 8 o'clock and I'll just be hanging out all night. So feel free to join me if that would be helpful. You don't have to, I think some people have this idea, well, if I go to office hours, I have to have questions. No. You do not have to have questions. You can just come hang out. You can be a fly on the wall, listen to other questions. If you just need to be sort of disciplined to like, okay, my professor's here, I better get something done kind of mindset. If that helps, great. Like whatever it takes. But don't feel like, oh, I can't go to office hours because I'm going to be expected to ask something. Not necessarily. Just feel free to take it or leave it as much be helpful, whether in Zoom or in person, either way. And then on Thursday, our exam is on Thursday, so I'm hoping by Thursday we're getting things in pretty good shape, but I am still going to show up at about 10 o'clock and I'll stick around until I have to go to my other class at 12:30 roughly. So that'll be a chance to ask any last questions as well. So these are going to be my office hours. I've pulled up the Canvas page here just to remind you again that if we go into the files section of the Canvas page, I know that might be a little hard to read, but there is a folder here that says second midterm resources. I'm sure many of you have already found this. There's a bunch of stuff in here. This is all totally optional. So the point here is you can take it or leave it, but I have 2 sample midterms here. Both of them have, of course, the blank exam and then also the solutions, which I would recommend trying not to just look at the solutions. Be better to try the exam first and then compare with the solutions. But there's also a review session that has a video, by the way, that goes with it. So if you feel like watching me solve through, I think it's like 8 problems or something I have in that. It's like a 2-hour review session that has about 8 problems in it. You can watch that, or if you'd rather not watch it, you can just read the solutions. I typed them up as well. So whatever's better for you. Sometimes listening is helpful, but other times you want to just look something up quickly, you can just look it up in the document here. There you see the quiz solutions. I put those in there just today. So the solutions to that extra credit quiz. And then the review packet. I think I mentioned this before, I think it's not a bad idea to go through that packet with the bullet point list. Here's all the things to be able to do. Make sure you can check them off. My guess is that if you can check off that bullet point list and you maybe try one, if not both of the sample exams, you're going to be sitting in pretty good shape. And if you've at somewhere along the line there, you're like, oh, wait, I don't feel so good about such and such and such and such. Then you can go look at the review session, find some discussion about it or a problem that's similar to it. And I hope that that will help you out as well. So, and then if that's still not making any sense, you can also come talk to me. So anyway, lots of ways to get help here. James?
Those sample midterms that are in there right there.
Yes.
That will go over specifically what we're gonna be.
Exactly, that's
like a
the,
6.2
I teach
or-
this class
Okay.
like a carbon copy every single time. So the last time I taught the class, whatever those old exams are, they are exactly lined up with these same sections, same breakdown, everything. Yeah. I actually think in this part of the course, there's not as many things to memorize in terms of like formulas. But what there is in this part of the course is a lot of focus on exactly writing out and communicating your your solutions very clearly, right? So if you want to show that something is a subspace, I would say on that take-home quiz, the first problem where I had you prove that you had a subspace there. If anything, that was the one that people didn't do quite as well on. Overall, the quiz was fine. But if I made any notations on your paper about that, you might use that as a little suggestion to practice it a little bit more. Just how to write out some of these abstract proofs. I think that's sometimes more the challenge here than a bunch of formulas to memorize. Heck, the hardest formulas in this whole section are really the Gram-Schmidt formulas. And I think I told you last time, I'm going to give you these. So these will be provided, these Gram-Schmidt formulas. So you don't need to memorize these. You just need to know when to use them, basically. So that is kind of my thoughts about this. I don't have anything else. We just have the homework due tonight, which I'm going to help you with. My goal is to get you guys done with that homework so you can really have the full 2 days to study. And then don't really have any homework planned for the upcoming weekend. That would be shocking. We just take a couple days off from this class. I don't know. I'll give you something you can look ahead if you want to, but it's not going to be a real heavy weekend for this class. You'll get a chance to kind of maybe sleep a little bit, something like that. We'll see. Anyway, so yeah, and for today, I'm going to mostly be reviewing. As I said, we've done a lot of hard work to get into position for this exam. So I think we can spend some time. Does anybody have any questions about anything about the exam or kind of what this next couple of days is going to look like? I won't write the exam till the last minute. So I always do that. I'm kind of a last minute guy. So I can't tell you a whole lot about it yet, but other than what I've kind of as a general outline of it, I've kind of given you an idea. So anyway, I'm around to help. I really want everybody to do well. We're not competing with each other. I can't only give so many A's or B's or whatever. No, I can definitely try to see everybody doing well in the exam. That's what I would really like. So just you just have to pull up your end of the bargain, put a little time into getting ready for it, and let's just see how things go. So what I guess I'll start with today, I did put up a recap over here, and this is just a quick reminder about this Gram-Schmidt process. You definitely want to know what it's used for and when this might come up. This is from 5.3, by the way. That's where you'll find it in the book. This is a process that replaces a set of vectors with an orthogonal set of vectors. And I kind of drew some pictures last Thursday to show how that works and to derive these formulas. The original vectors are V1 through Vn, and the new orthogonal set is W1 through Wn. And just remember, orthogonal sets of vectors are so nice to work with. Your standard I, J, K vectors in the coordinate plane, in the coordinate space for R3, you relied so heavily on those just in your calculus classes, right? And it's because they have such computational simplicity that it's so worth it. It's so worth it to play with an orthogonal set. So that's why we want to use this process, to take a perhaps less than ideal set of vectors and replace them with a much better set that are all mutually orthogonal to each other. And so I've got the formulas here for how you replace V1, V2, and V3 with W1, W2, and W3. I mentioned last week that I would not ask you to do more than 3 vectors for this process. I think most of the homework is just 2 vectors actually, but at most I might ask you to do up to 3 of them. And it's really just a matter of sort of just taking a breath, looking up these formulas and making sure you know how to calculate this. The inner product is showing up in the formulas. So remember that normally that formula has to be given to you on whichever problem it is. They have to give you that inner product formula to use. If the only situation when they might not actually explicitly give it to you, I mentioned this before, just to remind you, that would be if we were using the regular dot product in Rn. So in that case, if you have some vectors in Rn, I might not explicitly give you the formula. Did you guys all watch that little 9-minute video that I had you do? I think I told my grader to instead of giving you completeness points, I said just give them the points if they put the notes on the video into their assignment. So I hope that everybody got those points on that last homework assignment. But you might have noticed the first example in that video was vectors in R4. And I didn't have an inner product formula provided. Is because you're supposed to just assume it was the dot product. Yeah, so that's the only exception. Otherwise, you have to be given these inner product formulas, which of course is related to the norms as well. And yeah, you just crunch away with the numbers. You just do the calculations. And be sure to read very carefully because there's also the concept of an orthonormal set of vectors. In that case, you first want to orthogonalize the vectors, just like I've been discussing. But as a second follow-up step, then you would need to normalize each vector. That amounts to dividing each vector by its norm. Okay, so that is also sometimes going to come into play. So read very carefully on Thursday. If I say something like find an orthogonal set of vectors, then you don't need to normalize the W vectors that you come up with. But if I ask you to find an orthonormal set of vectors, then you have to not only find the orthogonal vectors first, you then have to normalize them. Clear enough? Pretty straightforward. Okay, so anyway, yeah, so this is the Gram-Schmidt process here. And there's a couple of problems on the board over there. Maybe we could start with taking a look at those. And that'll give us a chance to practice this Gram-Schmidt process together. So let's do that. Let me actually start with number 21. I see there's 2 questions over there so far, but let me just start. So we're going to spend a few minutes taking questions here, guys, on this homework that's due tonight. So 5.3, number 21. And what it is they give you a couple of matrices. So A1 is the matrix 1, -1, 2, 1. Okay, it's a 2 by 2 matrix. And then the second matrix is going to be 2, -3, and then 4, and then 1. Okay, and what it asks you to do is to make an orthogonal basis for the span of these vectors. So the vector space V that we are working with here, guys, is just the span of A1 and A2. And A1 and A2 will be a basis for V. Can somebody explain to me why? I know that A1 and A2 will be a basis for V. It's a span tells me that this will be a vector space. It will be a subspace of, I guess, M2 of R. But why do I know that A1 and A2 will be a basis? If you had to explain that succinctly, is there a reason we can give here? Not necessarily, Brighton.
Because it's not a scalar multiple of each other.
Okay, these 2 vectors, very good. These 2 vectors are not scalar multiples of each other. And when you have only 2 vectors, they are Li as long as they're not scalar multiples of each other. Now that doesn't work for 3 vectors, 4 vectors, 5 vectors. But if I have only 2 vectors, as long as they are not scalar multiples, so that means you could take one of them, multiply it all the way through by a constant and get the other one. As long as you cannot do that, then the vectors are Li. And that is the case here, right? So A1 and A2 are, let me just make a quick little note here. This is not part of the homework question. I just want to review for the exam, right? The note here is that A1 and A2 is Li since they're not scalar multiples. Okay, just be careful not to overuse that justification. That does not work if there's more than two vectors. But as long as there's only two vectors, we can just say, look, they're not scalar multiples of each other, so therefore they are Li. Okay, so they're Li. What's the other part of being a basis that we would have to have? They have to span the vector space, right? They have to span the vector space. Or can I use that thing about the K value versus the dimension? So K, let me just remind you about that. So K is the number of vectors that it gave you. So in this example, K is 2, right? What about the dimension of the vector space? That's actually the tricky part. We've never seen this vector space before. By the way, the big universe of M2 of R, that's not what V is. I'm not calling V M2 of R. If it was, if V was equal to M2 of R, then this would not be enough vectors to be a basis. Because you probably remember that the dimension of M2 of R should have been 4. And that's only 2 vectors. So these vectors would not have been able, remember how if K is less than the dimension of the vector space, then they cannot span that space. Those vectors cannot span that space. So these two matrices, they cannot span M2 of R. They're not going to be a basis for M2 of R. But my question is, are they a basis for V? And V is a different creature than M2 of R. What is V? V is the set of all possible linear combinations of A1 and A2. That's what span means. So it's actually a subspace of M2 of R, but it's not the whole M2 of R, is it? It's only those 2 by 2 matrices that you can express as a linear combination of A1 and A2. So why do I know that A1 and A2 will span V? It's because it's exactly what V was created to be. V is, by the way I set this up, the span of A1 and A2. Guys, a set of vectors will always span whatever they span. Okay, it might not be the whole M2 of R, but these two vectors, A1 and A2, they will span whatever their span is, which in this case I'm calling V. And so this is automatically a spanning set. Okay, so almost by the definition of what my vector space is, this is a spanning set sort of just for free. It is a spanning set for free. So I'm just going to say that A1, A2 is a spanning set for whatever it spans. Whatever it spans is, i.e., V. And that is what V is. If I actually wanted to know what V is more concretely, it would be a bit of a challenge. Like I wouldn't be able to, like if I gave you a matrix, 7, 8, 9, 10, and I asked you, is that in V? I wouldn't be able to answer that in 2 seconds. I would have to think about it. I would have to see, well, I wonder, can I write this vector as a linear combination of these two? That becomes a whole big set up a matrix and do some EROs kind of problem, right? So it's actually not clear exactly what V is explicitly, other than to say that it is being defined as the span of those two vectors, A1 and A2. So by its very nature of how I constructed it, right, those vectors are a spanning set for V. By the very nature. So they're a spanning set, they're Li, so they're a basis. So this is a basis for V, but what we want to come up with is an orthogonal basis. That's what problem 21 is. Okay, so for the orthogonal basis, now I think I'm ready to actually get into the homework. Is there any question though so far? I just wanted to, this kind of goes back to the chapter 4, I just wanted to remind you here. But if I'm not making good sense, you should stop me. I just want to make sure.
So if one of them was missing, it would not be a basis. If it was not LI, it would not be a basis.
If it's not LI, it's definitely not a basis. Yeah, exactly. So they have to be LI and a spanning set. But whenever you, guys, so here's the long story short. Whenever your vector space is created as span of blob, the blob is already a spanning set, right? Whatever you've put into that list is a spanning set. The issue will be, are they LI? And in this case, it's no issue because they're not scalar multiples of each other. I'm sure that they are LI. But that would be the only issue that you could ever have. But they're always going to be a spanning set for whatever they span. So if you create your vector space to be that, it's a done deal. They are a spanning set. Yeah, great. Okay, so that is that. Now let's do the orthogonalization part. So I have to set up the W1 and the W2. So W1, as you know, is just literally the same as the V1. In this case, I'm calling it A1. So the first matrix would just be the same. So it's just the same matrix again. And then I have to do the W2. And for W2, I take the second vector, which is the matrix 2, -3, and then 4 and 1. And I have to subtract, so I'm using the formula here that I'm going to give you. I have to subtract, okay, this is going to take a little bit of writing, so give yourself enough room here, guys. Don't try to crowd this in. I'm gonna put my W1 matrix over here on the outside, and there will be some number in front of it. And this number is just coming from this inner product, right? So we have to do the inner product of the two matrices. So let's just write that down. The inner product of V2, which is 2, -3, 4, 1, with W1, which was 1, -1, 2, and 1. So I'm going to have to calculate that. I'll do that in a minute. And then in the denominator, we have the norm of W1, which is the matrix 1, -1, and 2 and 1. The norm of that matrix squared. So keep in mind that everything, it looks horrendously messy here, but everything that's here is just a number. It's just a number, right? So we have a numerator and we have a denominator. How do we calculate this inner product right here? Careful.
They give us an equation.
Don't they give us an equation? Guys, this is not Rn. Okay, this is 2 by 2 matrices. So we're not in a world where there is a dot product. There is no such thing here. So we have to rely on them to give us this formula. And they did. They did. So if you looked at it, I've had people come up to me and say, where's the formula for the inner product? It's 5 lines above the question. It's kind of hiding right above the problem. So the formula, maybe I'll write it down here. They give it to you in the book. They give it to you in the book. And what does it say here? It says 5A11B11 plus 2A12B12 plus 3A21B21, and then finally plus 5A22B22. That's given. In the book, they actually give you that equation, and that's the one you're supposed to be using. Okay? So let's do this inner product of these two matrices using this formula. So using this formula, I'm going to try to squeeze it in up here, guys, if I can. We have a factor of 5 times A11 B11, which would be 2 times 1. So 5 times 2 times 1 plus the second one is 2 times -3 times -1. Okay? And then the third term is plus 3 times A21 B21, which is 4 times 2. And then finally plus 5 times A22 B22, which is 1 times 1. So now you just have to put on your calculator hat and figure this out. It looks like it's going to be 10 plus 6 plus 24 plus 5. Is that 45? I hope so. If it's not, I'm still too tired. Didn't sleep enough. I think it's 45. 10 plus 6 is 16, add another 24 to that, it's 40, add 5 to that, you get 45. 45, so that's on top, okay? Now, on the bottom, I have to do the square of the norm of this vector. So I hope everybody remembers that if you want to find the square of the norm of a vector, that is just the inner product of that vector with itself again. So this goes back to the first part of chapter 5. So what we're going to do here is calculate the inner product of this matrix with itself. So I have a factor of 5 times 1 times 1, right? 5 times 1 squared, and then plus 2 times negative 1 squared, and then plus 3 times 2 squared, and then plus 5 times 1 squared. Okay, put an equal sign there. And now we just have to crunch this number out, right? Have to crunch that out. It looks like it's 5 plus 2 plus 12 plus 5. 24? I think it's 24. That should be 24. Okay. So my correct answer for W2, let me maybe put it down here in blue. W2 is the matrix 2, -3, or 1, minus 45 over 24. That can be reduced, by the way. I think it's 15 divided by 8. If you simplify that, times the matrix W1, which is 1, -1, 2, and 1. Okay. And I will let you, so as I said, this is 15 over 8. Cancel out factors of 3. I will let you guys maybe do one step and just simplify. If you want to check the answer in the back of the book, you're going to have to actually do that subtraction. So I'll let you do that. It's not a big hard thing at all. But that's how you do that. So keep in mind that they had to give us this inner product, and it may not look like a natural inner product. In fact, you've never seen it before. Okay. Technically, before I asked you this question, if this was on an exam, the first part of the question might be verify that this is a valid inner product. Remember the axioms? So that is something you need to memorize. The axioms of an inner product, you would have to verify those axioms. And then maybe part B of the question would be, okay, now that we know we have a valid inner product, let's use it to create an orthogonal set. And that's what we just did right here. My final answer, for your final answer, guys, on this problem, it would be a good idea to make it into a set. So sorry, I should have added one more last thing here. Let's actually make it into a set of vectors. So you write down W1 and W2 into a set. And I don't know what W2 is yet. Whatever. I'll leave that part to you guys. Okay, good enough?
Question.
Please.
Let's say in an exam, you say, oh, verify the axiom.
Mhm.
Let's say we skip that part and then we just go, because we don't know how to verify it. Do we still get point for the second part if we do the
I always grade the parts of the exam independent from one another. So yeah, I would definitely just go on to the next part, but I'd also be crying while I did that because you should already know that I might ask you to verify the axioms of an inner product. So you're going to know how to do it, right?
Yeah.
Yes, hopefully everybody is. Okay, good. All right, let's look at number 18. I see number 18 is up there as well. So we can do this one as a group as well. Number 18, we have, this is polynomials this time. F1 of x is 1, F2 of x is x, and F3 of x is x squared. And they give you some domain here. They don't worry about this notation too much. They call it C super 0 of 0 to 1. The super 0, that just means continuous functions on the interval from 0 to 1. And they tell you what inner product to use. If you read the question, it says, use the inner product given in equation, and then they give you the equation. What the equation is that you're going to take inner product of f and g by doing an integral from 0 to 1 of f of x times g of x times dx. Right. So that's a pretty standard formula to use for the inner product here. Okay. So let's run through this. I'll go a little quicker this time. I have to do F1, F2, F3. I need to replace them with W1, W2, and W3. And of course, W1 is just 1. Go ahead and put that one down immediately. Next, I go to W2. W2 is obtained by taking F2, which is x, and I'm going to subtract some scalar in front of W1. I'm using the Gram-Schmidt formulas on the left board there. In the numerator, I have to do the inner product of W2 with V1. Sorry, sorry. No.
V2.
I do the inner product of V2 with W1. And then in the denominator, I'll take the norm of W1 and I'll square it. Okay, this is not hard. Let me just do it right here. Both of these are just integrals from 0 to 1. So in the numerator, we're going to integrate from 0 to 1 of x times 1, which is just x. So that's just x dx. And then in the denominator, I'm going to integrate also from 0 to 1 of 1 times 1, which is of course just 1 times dx. Okay, the numerator gives me, well, let's see, when I integrate x, I get 1/2 of x squared. You evaluate that from 0 to 1, you'll get 1/2. The denominator is just x evaluated from 0 to 1, which is just 1, and that's times 1. So your final answer is just x minus 1/2. Sweet. We are already 2/3 of the way done. But probably work-wise, we're not even halfway done because it's usually the third vector that kills you. You can see the formula for W3 is the longest one. But at least by now you have your rhythm going, I hope, and you understand, okay, here's W1, here's W2. I'm just going to follow the formula to figure out W3. So W3 is going to be V3, which is x squared, minus, and I'm going to make a big fraction here. I have a 1 here. I'm going to take the inner product of V3. I'll just go ahead and put it in now. It's just x squared with 1 divided by the norm of 1 squared. And then minus the inner product of x squared with x minus 1/2 divided by the norm of x minus 1/2, quantity squared, all of that times x minus 1/2. So I'm using the W2 in that calculation. If you have a problem like this on the exam and you feel like you're getting bogged down in the calculations, honestly, finishing the problem from here is not going to make or break your exam at all. I mean, maybe it's worth a couple of points. I mean, honestly, out of the entire problem, we've already done W1 and W2. We've written down the formula for W3. If we just decided to punt and say, I don't have enough time, I'm going to go work on something else, and let's say you don't get around to checking out what these numbers are, I will already feel pretty good. The fact that you are using the right method, you've shown me how to at least go through the first part of the process. This would not be a make or break for you on Thursday. And so I'm just trying to give you guys a little bit of advice, just not to get so stressed out about it, right? It's really, this is just crunching numbers here, right? That's all this is. So let's just go ahead. I will do it. W3, it's x squared minus, and again, you'll have to do a couple of integrals here. The integral on top is from 0 to 1 of x squared dx. And the integral on the bottom, actually, we already know what the norm square root of 1 is. That came out to 1. We did that earlier. So that's just a 1 on the bottom. We have a 1 right here. Okay, and then we have to do one more calculation, which will be some multiple of x minus 1/2. These are just baby integrals that we have to work out. So this will be an integral from 0 to 1. What do we have here? The inner product of x squared with x minus 1/2 So when I multiply those together, I have x cubed minus a half x squared. I have to do that integral still. I'll come back and do that in just a moment. And then in the denominator, I have the integral from 0 to 1 of x minus a half quantity squared dx. That's gonna be the whole thing. All right, so let's see, we have x squared, and then when I integrate x squared from 0 to 1, I get 1/3, right? I get 1/3 evaluated from 0 to 1, which is 1/3. That's just 1/3. And then here, okay, here's where all of the rest of the marbles are, is just getting these things calculated. In the numerator, see, even I don't want to do it. Integrate x cubed, you're gonna get 1/4, right? Luckily, the limits of integration are really nice, okay? You can thank me for that. I've just made nice, easy limits. So it's a 1/4, and then minus, let's see, when I integrate half of x squared, I think it's 1/6. Yeah, I think it's gonna be 1/6. And when you evaluate it from 0 to 1, so 1/4 minus 1/6 on top. On the bottom, little asterisk here again, I'm gonna do this integral down here. X minus a half squared. You can either do it using a little u substitution, or you can just multiply this out. I think I'll just multiply it out. So if I multiply this out, I get x squared minus x plus a fourth. Did I make a mistake? No, I think I'm okay. I think I'm okay. So we have that, and then when I integrate this, I'm gonna get 1/3 minus 1/2 plus 1/4, right? That should be the way the numbers shake out, and I think I'm gonna need a denominator of 12 to clean this up. So that's gonna be 1/12, I think. It's gonna be 1/12. Okay. That's 1/12. What's in the numerator? Let's see, is that also 1/12? Yeah, 3/12 minus 2/12 is 1/12. So guys, that all cancels. See, totally don't worry about it. So all you get is x squared minus 1/3 minus the quantity x minus a half. So if I clean that up, I would have x squared minus x, 1/2 minus 1/3 is 1/6. So this should be W3. I did it really fast, so I hope it's right. If it's not, did you check it? Okay, good. I've got at least one confirmation. If not, we'll all lose points on the next homework, including me. But that's okay. Questions there? Okay, super. While I'm on the topic of this assignment, did anybody want to ask me about any of the other problems that you're working on for tonight? Vinny? Yeah.
The answer to that would just go on a set.
Oh, I'm sorry. Yeah, just like I did the blue set here. Yeah, my final answer here, I should have written it as 1, comma, x minus a half, comma, x squared minus x plus 1/6. Okay, and again, we're kind of lucky here. They're not asking us to normalize these vectors. If you had to normalize them, you would still not be done. You would have to find the norms of each of those and put those as denominators of those polynomials. Good point.
Can we do 15 or 5.2?
Sure. Let me go back to 5.2. Let's take a look at number 15. Oh, this is a little intimidating because they have all these fancy words about Legendre polynomials and things like that. But none of that actually matters. So yeah, number 15 is not all that different than the one we just did. We have f1 of x equals, this is from 5.2. f1 of x equals 1, f2 of x equals x, and f3 of x equals 1/2 of the quantity 3x squared minus 1. And they ask you to show that these vectors are orthogonal already. But of course, let's be careful. We can't decide if they're orthogonal or not until we have an inner product in our hands. And what I wanted to mention here is that the inner product that they're going to use on this problem is actually not quite the same one that we used over there. Because they give you limits of -1 to 1, if you look at the question. So we do have to do this with respect to slightly different limits of integration. I think I mentioned last week that all you have to do is sort of tweak up the angles between vectors and make things orthogonal or not orthogonal, is just change the limits of the integration. Because then all of your numbers change. And so what was orthogonal before is no longer orthogonal and vice versa. So it's a little sensitive to the exact formula for the inner product. This is always going to be very, very sensitive to that. Okay, and all it's asking you to do here, guys, is to show that these vectors are orthogonal as a set. So what do I need to do here to show that?
Plug in the function.
When I plug these functions into the inner product, I have to get 0, right? That's what orthogonal means. So I just have to just calculate it. What is the inner product of F1 and F2, right? And then what is the inner product of F1 with F3, right? And then finally, I'll do the inner product of F2 with F3. I have to do all of these and just make sure it comes out to 0. Like we know what the answers has to be. If this is an orthogonal set, all of these answers have to be 0. So on the first one, for example, we're going to integrate from -1 to 1 of the product of the first two functions, 1 times x, right? So it's just that integral right there. Okay, of course, when you integrate this, you get 1/2 x squared. When you evaluate it from -1 to 1, it all cancels out because the x squared makes everything positive, and you subtract the two limits, you get 0. How about F1 with F3? That's going to be the integral from -1 to 1 of the first function times the third function. There's a 1/2 of the quantity 3x squared minus 1 dx, right? And I'll pull the 1/2 out of my way, and then I'll just anti-differentiate 3x squared minus 1, which I think we can all probably do pretty easily. It's just x cubed minus x. And I've got to evaluate that from -1 to 1. Actually, you plug either of those limits in, you end up canceling, the subtraction cancels those values out. So this is also 0. We know the answer has to be 0. Okay, so that's going to be the case. And then the third one is the integral from -1 to 1 of F2 times F3. So I'm going to have a 1/2 x times the quantity 3x squared minus 1 dx. Again, I would probably pull out the 1/2. I would probably also just multiply the x inside. So I'll write one more step here. I'll actually be integrating 3x cubed minus x this time. Okay, and that should also be 0. That should also be 0. So we'll just say that it's 0. Let you guys confirm that if you want to. It's pretty easy. Okay, so that's the first thing. Then actually the harder part of number 15 is they then say to construct an orthonormal set. Oh, by the way, do we need to use the Gram-Schmidt process on these vectors? No, if you remember, the Gram-Schmidt process is used to make an orthogonal set of vectors out of a random set. Well, if these are already orthogonal, I can guarantee you what will happen when you use the Gram-Schmidt formulas. Actually, you guys can tell me as well. Because if the vectors in question are already orthogonal, then that means that these parts would already be 0, wouldn't they?
Oh,
And so W1 is already equal to V1, and look what W2 would be. V2, and W3 would be V3. So replacing V1, V2, V3 with W1, W2, W3 would do nothing, right? You would literally just have the same set of vectors. There's no point in using the Gram-Schmidt process if the vectors are already orthogonal, right? It's just going to be a waste of time. It's not going to get you anything different. So yeah, we don't have to do the Gram-Schmidt process here. And in fact, this is section 5.2. Technically, we didn't even explain the Gram-Schmidt process until the next section. So We don't have to do that, but what we do have to do is the normalizing part. Okay, so they did ask us to normalize these vectors. So that means I've got to find the norms of all of these vectors. I'll start with the first one here. I might not do all three of these. We'll see how tired I get. The norm of a vector is just the square root of the inner product of that vector with itself. Don't forget about that square root. It's very, very required. And so that square root is going to be above this integral now from -1 to 1 of 1 times 1 times dx. And guys, that comes out to be the square root of 2 when you evaluate it. So my first normalized vector, I'm going to call it u1, would be 1 over radical 2. So you take the original vector and divide it by its norm. So if its norm is the square root of 2, you make a denominator out of that. Okay, so that's the norm of f1. I guess I'll do f2. I'm gonna probably stop after that. The norm of f2 is the radical of the inner product of f2 with itself. So this is the square root of the integral from -1 to 1 of x times x. The same function goes in twice, so that's x squared, right? And when you integrate x squared, you get 1/3 of x cubed, and when you subtract from the top limit to the bottom limit, you actually get 2/3. So you end up with the square root of 2/3 here. And so my second unit vector becomes f2 divided by its norm, which is the square root of 2/3. I think in the back of the book, if you check the answer, they actually flip that over and write it as the square root of 3/2 times x, like that. But either way is fine. So this becomes u2. And u3 is a little more of a pain. You actually have to take this third function and multiply it by itself and then do an integral. I think I'll let you guys check that one. It's not too big of a deal. This is an odd numbered problem, so you find the answer in the back of the book, and I wouldn't recommend spending more than a minute or two on it. Okay, so there's a lot to do here, actually, but none of it is that difficult. None of it is that bad. Right. Questions? We're feeling okay with chapter 5? Well, I might try a quick question on you. It's actually one of the recommended problems, so I'm not sure how many of you are working through these. Sometimes in the homework, I have the required problems and then I have some recommended ones. There was a recommended one in this chapter that I never did, and it's a proof. You should expect some proofs on Thursday. It's not all going to be crunching numbers. I will want to see if people are understanding the concepts as well. And so to do that, all I have to do is kind of move over into the realm of abstractness, and then everything becomes conceptual. So there's a problem in here that I kind of liked that I thought I might try on you. So I'll set the homework down for now. Okay. Again, if there's more questions on it or you're still working through it, I'll be around tonight. You can certainly ask me later. But let's just do, I guess I'll just call this a warm-up problem for today. I just want to try to prove that if you take the norm of, let's say, v plus w and you square it, and then you add that to the norm of v minus w squared, I'd like to try to prove that that gives you 2 times the norm of v squared plus the norm of w squared. So again, I don't know if you have been looking at the recommended problems, you might have already seen this one, but if you haven't, then we can give this one a practice run. I think I've actually put this on an exam before, so it's at the right level, kind of the right level of challenge, I think. But you see, it's totally abstract. They didn't actually give us an inner product formula, so we're not going to be crunching numbers using an inner product. But what we have to do instead is use the properties of inner products to try to prove this, right? So let's see if we can do that. I'll do this in blue. I don't think we need too much room. It's not like, usually these theoretical ones are fairly short. It's just, it's gotta be the right thing. So I'll just start with the left side here. The square of the norm of v plus w, and then I'm gonna add that to the square of the norm of v minus w. Would we have any idea how to do anything with that?
Break out a square.
How do you do that?
I'll like, b plus w times b plus w.
Okay, I'm gonna use some different language. We're gonna take the inner product of the vector with itself, right? So if I see the square of a norm anywhere, anytime, on anything, that means I'm gonna take the inner product of the vector with itself. So the inner product of v plus w with v plus w. And then I'm gonna add that to the inner product of v minus w with v minus w. So this would be the idea. They're just to replace those norms with inner products. Basically using this. The square of any norm is just the inner product of the vector with itself. Be sure you're using this correct notation. I see people do stuff like this. Oh, this is v plus w squared. I'll see stuff like that. And I'm looking at it and saying, so you're telling me you're gonna take this vector and square it? And I'm like, what does that even mean? Like, I know how to add vectors. I know how to do scalar multiplication, but I do not know how to take one vector times another vector. So you gotta be real careful with your notation. That's actually one of the bigger issues with these kinds of abstract exercises with inner products. So we're gonna leave it like that. And now what can I do though with this expression so far? Is there anything else that anybody has a suggestion here where I could go next? Yeah, we can FOIL it out, and by FOIL, what I mean is we can use the inner product axioms to sort of break apart these plus signs and create more terms, right? So for example, the inner product of v plus w with v plus w could be thought of as the inner product of v with v plus the inner product of v with w plus the inner product of w with v plus the inner product of w with w. All of that is just the first part. And as you can imagine, the second part I could treat exactly in the same way. So I would have the inner product of v with v again. And now I have minus signs this time. So minus the inner product of v with w. And then minus the inner product of w with v. And finally, a double negative on the inner product of w with itself. So we are using, this is really going back to section 5.1. We are using the axioms of an inner product here, guys, to manipulate this thing. Okay. Does anybody see any ideas what I could do with, this is 8 long terms here. Can I do anything with that? Let me hear from some other folks here. Somebody who hasn't had a chance today, wanna give me an idea here, Edgar?
Combine VW and WB. Because they're practicing too.
Yeah, there's these two here, we can combine, right? So let me do that. So I'm gonna go ahead and just put them here. So 2 copies of v plus w, that was an axiom, right? That the inner product of w with v is the same as the inner product of v with w. So I can do that. What else could I do? Carlos? Over here? Oh, these two. These two are identical, right? Inner product of w with w, I have it twice. Let me write that down. I'll put it over at the end. 2 copies of the inner product of w with w. So that takes care of that vector and that vector. We already looked at these two. What else can I do? Okay, here I have the inner product of v with w and the inner product of w with v, which are the same. There's 2 of them and they're both subtracted, right? So I can do a minus 2 factors of, again, v with w. All right, what else? I took care of those two. What have I not checked off yet? Girls? 2 copies of the inner product of V with itself, which is just the square of the norm of V. So this is the norm of V squared, and there's 2 of them. Right? So actually, what happens, guys, you probably noticed it already, that term cancels that term. And what am I left with? Well, I have 2 copies of the norm of V squared here at the beginning, but I also have 2 copies of the norm of W squared, which is the term at the end. And that's exactly what I'm trying to come up with. So it absolutely, completely 100% cancels out. It gives you exactly what you're looking for. It's kind of interesting. If you're wondering about this property, it's kind of some kind of a parallelogram law. If you have, let's say, a vector here V and another vector here W, just so you can see it, this is not that critical, but just so you can kind of appreciate it a little better. Here's another copy of W and here's another copy of V. And if you think about it, the right-hand side is calculating the perimeter of the parallelogram. You have a length of V plus length of W plus length of V plus length of W. Well, that's just the right-hand side. 2 factors of the length of V, 2 factors of the length of W. It's literally the perimeter. This is not a very good parallelogram. It's supposed to be, let me see if I can try. I pride myself on my sketching. Something like that, right? So that's a little better. So the perimeter going around the outside is actually what's on the right side here. Okay. But what's on the left side actually is very interesting. V plus W. V plus W is actually this full diagonal length going from the head of the first, sorry, the tail of the first vector to the head of the second vector. So that's V plus W. Well, it's the square of V plus W. And V minus W is actually the other diagonal. Because it's like taking V plus the negative of W. So if you took V plus the negative of W, which should just go the opposite way, you would literally get this vector. So the left side of the equation is actually the squares of the diagonals of the parallelogram added together. And the right side of the formula is just the outside perimeter of the parallelogram. I never taught geometry. Did they ever teach this? I don't know if you ever saw it or not. Anyway, I don't know, but it's just kind of a nice thing that we can use inner product space material to justify, is that there's a relationship between the lengths of the diagonals of a parallelogram as compared with the perimeter around the outside of the parallelogram. They are absolutely related to each other, as this kind of shows for any parallelogram. Okay. I think I'd like to take a 10-minute break, give everybody a chance to stretch their legs and whatnot. When we come back from the break, we're gonna do a little group work. And as I said, I might start the next section just to talk a little bit about it. We won't do too much with that. So I'll see you guys in about 10 minutes. We'll pick things back up. Can you erase that 18 and 21 off of there for me? Thank you. Since I've already done them.
And then there's more, we should just go to the office hours.
I think so. Yeah, I think probably that would be best at this point. I'd like to do some other stuff.
Okay.
It's also things. Because you're this times itself. Yeah. So you don't have, so it's alternate. Yeah, then I just have that. Yeah, just-
You do. Solve it. I know.
Because I don't think like. Obviously it matters, but like.
Okay, that's great.
I don't know if I did it wrong.
Yes.
Yeah, she don't.
Oh, you need to do it. Yeah, you need to do it. Yeah, you need to take some. Lay those vectors into the columns.
I got all this stuff.
And then.
It does. Kind of. I don't know.
Yeah, I didn't grade it too largely.
Okay.
People gave me the basis of it.
Oh, maybe.
Yeah.
I
Yeah,
was
cause.
generally okay with it. There's actually even another way.
But if you just speak.
Well, no, that's. Okay, there's three vectors here. What I can do is I can say, well, there's sort of only two vectors here. So these two by themselves are L.
Okay.
And it's tell just by looking at them, they cannot get an executor. So that, what that means is that if I pay another $1,000 for a vector that hasn't executed in it, that won't be a waste. That won't be creating a difference. Because I know that executor cannot be expressed in terms of. So that's a little more of a sophisticated reasoning. If you don't like that reasoning, you can always just put them into the columns of the matrix and go through the motions of the EROs again, which is fine. A lot of students would just do that, but it's nice to sort of appreciate it from a different perspective too.
Either way, we have to check for.
You technically should, you technically should check for LI. Yes.
I wasn't sure.
Yeah, I mean, I would always recommend to never erase anything on something like that, because especially if you're not sure, like, or maybe I need to put it, maybe I don't. When in doubt, it's always better to over explain. If it's on your paper, then I can give you credit for it. If you erase it, then it's like, maybe she had some idea, but I don't know. I can't guess at something like that. Yeah. Sure.
I didn't think something. Yeah. I'm just not sure, like, I don't think. Well, I don't have it. I wasn't sure.
Yes, listen. We're gonna practice. Okay. Sunday. Is it gonna be sitting with you, Anthony? Yeah. Oh, it was. Oh,
Yeah, I think so. I remember it.
Oh, I should have done it. Didn't remember that.
Good reviews.
Yeah, exactly.
Oh, the rank. Right. That's what it is.
I think it's
What's left over?
they're gonna get
Oh, okay, now.
That's good, but.
Oh,
Yeah.
Oh. That makes sense, yeah.
Yeah.
So polynomial?
No.
Yeah, no, I thought it was, I thought it was because of the sweet.
Well, it's more, it's more N, but it is vectors.
Oh, good.
It is vectors, but it's on coordinate.
Not these kind of
vectors.
Okay.
So I got.
Not my weird abstract vectors.
No, did that really help with that?
Yeah, we're doing a lot to do.
But I got that one.
Yeah.
Oh, yeah. I thought it was.
This is the knowledge. Yeah.
But I understood. I'm trying to see like when everything. You always have to put something in something else. Because they're gonna- And then,
Just give like a.
It's only bonus.
I thought.
Wait.
So look, so you have it. So you know, like, you get shows up.
This is how I study us. It's like V is equal to this. What is things how we go closer to it's V is equal to 1 or something. V is equal to P. Oh, yeah, P. So, yeah. And so right here, we got in the basis for this. That's the base of it. The big universe, right? They're like, there are 8 terms, so. Well, we can find the dimension of this.
Yes.
So when it's like this, you cannot
Make it
do like.
You're gonna
You're gonna get bigger. Yeah. This is. So then when you have it this,
Okay, guys, hopefully everybody's made it back by now. I have taken the liberty during the break of putting a couple of handouts on your tables, which are actually a couple of group works. And I'm going to give you guys about 20 minutes to find as many answers to these as you can with maybe a couple of partners. We're going to go use the whiteboards again, like we have done a few other times. I've given you a little guidance on what I might focus on. Of course, none of this is graded. This, whatever you get done is fine. I think the first 3 problems on group work 8 are pretty good. The last part of group work 8 we actually did in the homework, so you've already done it. And then for group work number 9, I would start with problem 2. I think 2 is really the best one. And then if you have a little extra time, you could look at number 3. But I'm only going to give you about 20 minutes to do this. So why don't you go ahead? There's markers all around the room. Grab 2 or 3 people and make your way to wherever you can find some open space. And I'll come around and check in on you as you're working, but see if you can get a little headway on some of these problems. My preference is to have as many people up at the boards as possible. I know it's not always feasible to get everybody up here, but let's do the best we can. Group work 8 and group work 9. Come on up, Nathan. I'll get out of the way. Yeah.
Oh, so you're also thinking as a.
Anthony, you have to have a group. I want you to work with people. It's actually good for you and for them. Okay, thank you. Don't be shy. Introduce yourself to anybody you want. I'm sure there'd be more, maybe those guys in the back, they don't have a lot of help back there. Plenty of room up here, guys. You want to work over here? Please. Sounds like a plan.
Oh, so you're saying.
Oh, just. Yeah. But, oh, yeah.
Yeah.
So it's hard to execute the program. Yes.
Yeah. Is it the same?
Yeah, this is 0.
Or just so far just.
That is the question. What we do, once we know what to do, answer that hard. Okay, guys, we are not checking substance. So it's not saying fine, that's not saying so this is. It wants you to find a basic. It just wants you to find a basic. You don't need to worry about like. Check.
So.
This is a quick. Super fast. You know what to do. The question is, do you know what to do? I know you guys all know all of the skills. Which of those skills are really right to be basis?
Because we were thinking of.
The thing about checking LI and scanning code, that's if you have.
You guys
Say,
said.
check, is this, is it LI, does it scan? We don't even have that. Let's find a basis in the first place. Great question. I will check back in with you shortly. Does anybody need help yet?
Do we need to check it with five?
Love it, love it, love it. Technically, so I just overheard your question. Technically, yeah, you want to be able to use the base. I'm gonna make a quick comment about it though. This mess is really the span of these three things. Which actually means that these are already spanning, you know, I was talking about earlier. These vectors are already span, whatever they span. So it is a spanning set, and we're also guaranteed that they are high. It may not be totally obvious, and you could put it into a matrix to check it. Like this first polynomial, x cubed plus an x squared, no x term, but you have a -3 constant, and you do that with these others as well. So you could put this all into a matrix. And then just make sure that you don't get any free variables when you reduce it. So let's not bother with that. It's just tedious errors to do that. But that would be one way to do it. Another way is just right here with an LI. If I only look at the second and third, should we just finish? Try to focus it here. If I only look at
I always
the
try
second
to,
and third one, they are not scalar multiples of each other.
make it.
So if it was just these two. Does this change that? Does putting this one in there change that? Well, I see X cubed.
What
And I know that I cannot make X cubed out of these two, because there is no X cubed. So I know that if I go and spend another $1,000 to pick up this vector here, I'm not wasting my money. I'm not creating a dependency. This vector cannot be written in terms of things. So if these two were Li to begin with, when I bring you another vector that cannot be written using the other vectors, then I can feel pretty good thinking that this is as good as I could, because some of these are Li. That's it. Yeah, it's really because that power is the power of X. Okay, so this is a basis, so the dimension of S is 3. So even though V is 4-dimensional, S is only 3-dimensional. Sweet, sweet. All right, good job, good job. You can go on to the next one. Anybody have questions so far?
The way I look at it, I'm like, okay.
Obvious. This is what's so challenging about material. I think, is that,
Well, the second question,
I
kind of distributed it and then.
doing the right thing.
Checking your standing.
That's if I already gave you.
I remember.
I said,
Well, if I mean.
Sorry, if I already gave you a set of vectors and I said, are then you would split them into a matrix. X, Y, or
Problem
I didn't give you any vectors at all. I actually gave you find the vectors. Honestly, you do not see it. Just taking this here. Besides trying to make it.
I've done it many times before.
I know you've seen.
I want my product to get sold.
What if that's a forward phrase? Bust out the variables. Exactly. Write down the form of the vectors, bust out the variables, and then just the vectors that are left over. This is kind of. Thanks for going back to everything. So that's what you need to do. Okay, so bust out the A, the B, by the way, the X is not a variable. It's only the A, the B. Okay, so eraser. Yes.
You're always. Those bases on this.
Oh, yeah, you would change the ABC, you would not change the X. Right, the X is sort of
Any idea?
part of the structure of the vectors.
Okay.
Yeah, that's exactly. So we're gonna check closure and their addition, and you have that polynomial as one of your vectors. Your second vector would be the same exact thing, but it's
Alright, so because that's what I do. I'm not always.
especially with polynomials, because you have the X in there. Oh, that's one of my variables. Actually, it's not. It's part of the vector itself. Yeah. Good question. Okay, guys. I'm gonna come screaming.
Yeah.
I'm gonna do that. So this is the form of the vectors that we. And our goal is. Oh, so like, all I can think about that is that you're trying to find vectors that, oh, I see. You notice that this has two columns. So I already know what my answer to this question is. So when I see R3, they might have been derived with good intentions and everything and so on, but they have not been written as vectors.
Dimension will be.
The way to do this.
Okay.
Is it the dimension will be more? So I just wrote basically.
Yeah, is that what you were gonna do?
Yeah.
Nice. It's okay. Right, so you're gonna bust out the A and say, where do I see an A of it, right? So I have an X cubed there, yeah, that's this one. Here's another A that has an X squared with it. And then there's actually one more A over here that has a minus T like, go like that.
Oh, yeah,
Go to
it's
the
a-
next
yeah,
one, do it again.
Yeah.
These guys here.
Okay.
These are gonna be your intersection. These are gonna be your base. They're gonna be your base. You can look at it and you can ask yourself, if you wanted to check with it. I don't see it.
I think.
Would be the way. Find these values. Okay. I already gave you a handful of and I said, are they?
Yeah.
Yes. I think we starting on the set and saying, fine. It's always if I say find a basis, find a spanning set, find a set, it's always that. Right? Like the vectors. Second step, bust out the variables. Third step. In this case, yeah, you can say it's five. It's not that one. I might ask you to check. I would have to be very explicit about what I said.
I will find resistance variables with even
The dimension of R is 4. What is the dimension of S? Focus forward.
Yeah.
Only, keep in mind, S is just. So P three of R, the big universe is 4-dimensional. We're not looking at the whole universe now, we're only looking at these polynomials here. It actually is smaller. It only gives me.
Yeah, like you all those. Have three for you.
Yeah.
What is that? Good job. Cool. That's what you said. Sometimes you. Oh, I gave you a list of that. Let's say that I handed these three polynomials, and I said, part of it. Yeah, you was,
I think that's when you would use it.
Circle my thing.
Okay. Yeah. Yeah, I think that's what that is.
I think we have to do that. Those three are like elements. I can double check.
The big thing.
That was great. Oh, you know, okay, yeah, the 9th entry.
Yeah, you got it right.
That last entry.
I got it right.
Yeah.
And then you can do with all the. Yeah.
Taking it like a-
Maybe I'll have check if it's LI, so then. It's good practice, but yeah. You that here. Sing out those variables.
We know we're gonna.
Yes.
So I'll set that to both three, and then we will have. There, one day we see it.
Yeah, technically, if you go there with the word stand in front of it, probably. You right now say.
I mean, I know it is.
I thought it has the right.
Oh.
Oh.
I thought that was down, but. But then I just. Which is what this is. This is showing you, oh, I get it in the car. Yeah. Which, by the way, is actually. It goes back to that. Instead of actually.
The ranks for the dimension of the. So like able to space
Try something else. Try number 9 and make sure you keep up. You guys doing okay?
You don't need to process out. You can say, oh, yeah.
How many periods of life? It's gonna get crossed off. You still have that. Oh, yeah. Take out. Does anybody need help?
I was there.
How we doing? Oh, guys. There is nothing saying that the rows add up to 0. There's nothing that says that the columns add up to 0. So, were you the one I talked to about this? Ah, you need to get up there and take that marker away from Zach. Show him what the right form. So you're doing the right process, but the form of your vectors is not quite right. That on the second one. That is not quite right because you are imposing too hard of a constraint. You're saying the first column adds up to 0, the second column adds up to 0, the third column adds up to 0, the first row adds up to 0. All these things adding up to 0. All 9 add up to 0. That's the only condition you have. So. You got it. He's got it. I'll let it. You guys doing okay? Okay, without any calculations, you can see, right? Second and third row get zeroed out. You've only got one pivot, so the rank is 1, and therefore the nullity is This is just reminding you about the rank and nullity here. So you take the rank of a matrix, add it to the nullity of a matrix. It always adds up to however many columns it is. So if I have 4 columns here, and the rank is 1, then I know that the nullity is 2. And I can do all that pretty much in my head. Okay. If you were asked to find the nullity, then that would be right. And then to get a basis, this would be another extra step. You would then put us and make our list. Why don't you guys try problem 2 from group work 9? Like it, give that one over. Anybody need a hand? Yeah, Steve got it. That's perfect. Yeah.
Yeah, they, these.
Or the null space. I think I'll make it fun. We're gonna write all the things. Yeah, one pivot, which is pivots is otherwise known as the rank. But not Thursday. A very, very important. Rank. Rank nullity here says that it's taking the number of pivots, that's the rank, and then add it to the nullity. Oh, that one. Then, and it's 4, and how many pivots do you have? 1, so what's the null? That's okay. I think you guys can do all that, we're gonna start looking at the dimensions. Now, normally the matrix isn't that nice, but this matrix is really nice, so you can see, oh, I can just kind of ignore the second row, and that means I only have 1 pivot. That was funny. Why don't you guys try number 2?
Yeah, good.
No, yeah, I think
Where you showed the zeros across.
So I want to go around this stuff.
I can just kind of see that, yeah, I mean, okay, anybody can have a bad moment and look at it and not recognize that's gonna get zeroed out. But I wouldn't worry about it. I wouldn't, and if you study for 500 hours, like, you can still miss that. It's not worth worrying about it. But if you happen to notice that that row's zeroing out, then that helps you figure out what the rank is. That was the I think that's a good one to practice. Anybody need a hand? Tiffany, that's looking great. Good job. Good job. Yeah, you guys got it. I like it. That looks really good. Looks good. Why don't you guys try problem 17 from group work 9? Group work 9. Yeah, I think that might be a good one to practice as well. Hey, how are we doing? Just pretty much boiling it out. I actually think we need to do this a little bit carefully. So if I foil this, the first one is this inner product with that. Inner product with. Okay. Then the next one is 3B inner product with 2B. Oh, I think the next one is 3B. Is that a B or a U? Oh, that's a U. We've also seen U with U. Yes.
Oh, yeah. If I remember correctly.
That's a base. Plus the inner product is 3U 2W. And then you foil with this minus the inner product W. And minus the inner product of W.
And you just do.
And then minus the product of W. So that's actually what you have when you foil it out. And now you're just gonna work this out. Work this out. Good so far? Yep, so far so good. You should probably have the answer within less than 2 minutes. It's taking longer than that. It's 4. How are we doing?
Oh, you're not dead. Okay, I'm sorry.
Yeah.
I want you to. Be bears, these characters. Not all triple over the-
Yeah, so I think.
That way you can have your three, see what people are coming up with. Right, so.
I know.
Yes. Oh, okay. It would be six, yes. It would be technically six because you can. Just so that.
What even is? Just count how many vectors are in your list.
I just combined these to make it.
So even though these are polynomials and
Has a bunch of messages here.
it's the substance.
That one there.
Substance.
This is just.
Oh, that's minus.
That's good. Why don't you try problem 2 from the group of analysis? You did, okay, sounds good. In that case, we can try problem 2. Yeah.
Yeah.
Okay.
This, I'm gonna. This.
Well, I probably did, yeah. Yeah.
These should be zero.
So I.
Yeah.
I
Sure, you're gonna be
Well, these are zero, so we're talking all sets. UV, zero, UW, zero. Just like you showed on the homework. To be orthogonal. Another has to be. So we just had negative.
That's crazy. I didn't see that. I was about to say crazy, man.
I can say.
I'm about to
are
do it.
by themselves.
And here, what? Say, oh. Random video right there. Trying to make sure it look good.
Very confident that they are.
Wait, officer running. I'm sure he is.
Out of these other two.
Oh, wait.
Oh, wait. Oh, yeah.
How did I not see it?
$1,000 right now.
Damn, I feel like I was doing this before. I was looking at sometime. Yeah. What else did you do? Oh yeah.
I am now looking to see the next step. This next step.
Got it. Yeah, you got it.
And if you need some help with it, I want you to all questions get every single word of that question.
Yeah.
One very.
They don't say what the name is.
I think you have it.
Some formulas that he gave us.
Did you pull out the make it optional then?
Two vectors are orthogonal. What is their inner product?
That process.
And they gave us that this is an.
Wait, if this is
set.
fancy.
So you know what most of those 6 terms? See if you can simplify them. Yeah. You guys doing okay here? That's the answer. You guys talk to the vectors are orthogonal. That's why you can cross off. It says. You know what, a lot of people have erased that. And they're like, what about the numbers for all of this terms? And actually,
How about this?
it's okay, it's okay. It's okay. At least now you saw it once and maybe. Everybody still doing okay here? Right, let's make sure we're using the inner product of the patient here. So this should be like, oh, that, and this is, see what you're, all that kind of stuff. Yeah, exactly. True. Already saw.
Oh, no, I'm just running course. Oh.
Because.
Not here.
Most of the time, like
It's like long as.
Oh, right now. That's great. Anybody need a hand? Well, on your way over there as well. I like it. Good job. Okay, and that's the right answer. Yes, I like it. Very good, very good. Good catch, good catch. You too. I was hiding that. Right. Yeah, exactly. You're trying to normalize. Hey, guys. We have like 5 minutes left. I'd like to kind of do, I want to do one more problem for you all before we call it a day. So even if you're not. done with your work, gather back up for just one more quick problem together and then we'll call it a day.
Oh.
Thank you so much.
What's tricky really, because I was done with the last problem.
Yeah, I think.
Oh, you got it. Yeah, but in this case, I went to the last one and I wasn't taking it all.
Yeah, I know.
Corner of your desk again. So just to remind you, it might not be a bad idea to go back to group work 6 and 7 and review those as well. 6, 7, 8, and 9. Those are the 4 group works and they're all in Canvas, including the solutions to those. And if you work out any of those problems again and you're still not feeling 100% solid, stop by my office hours. I'll be happy to kind of talk it through with you, which sometimes I think works better than just trying to read something off of a paper. So that is perfectly fine. But good job. I think most groups got quite a bit of those questions done that we just went over. I want to do one last problem today, and that's because I have not done anything today about linear transformations. And I just want to get it into your head again. And this is a nice problem that kind of combines chapter 4 with chapter 6. It's theoretical. And I think this is the kind of thing I would think is kind of appropriate level for you guys to know. So here's what we're going to do, guys. So this is one last example, and then we will call it a day. So let's let V be a vector space with basis V1, comma, V2, comma, dot, 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 up to Vn. And I'm going to assume that T, which goes from V to W, is linear. And And I'm going to also assume that T of V sub I is equal to the zero vector of W for each I. Okay, so this is my setup. I have a linear transformation from V to W. V has a basis consisting of V1 through Vn. And I'm going to imagine that when I transform any of the basis vectors, T of V1, I get 0. T of V2, I get 0. T of V3, I get 0. T of any basis vector is 0. What I would like to have us do, this is a proof. This would make an excellent little 5-point question on the exam, would be to prove that T of V is equal to 0 for all V in capital V. So let's wrap up today by just talking through this. This is not a lot of writing that we have to do. It's pretty quick. And I think I can just do the whole thing right next to it here. Try to do the solution. I want to prove that T will transform every vector to 0, not just the basis vectors. So if I know that T transforms the basis vectors to 0, I'm hoping to convince you that T would transform any vector to 0. Okay, so I'm going to grab this vector. So given this vector little v, I have no idea anything about it. It's just a vector from my vector space. Does anybody have any idea how I could show that T of that vector is 0? Normally, I'd give you a little more time to think about it, because this is a conceptual question, but since we don't have a lot of time, we only got a minute or so, I'm going to kind of spill the beans for you here. Remember, guys, that a vector space has a basis, and the basis is a spanning set for that entire vector space. What that means is that every vector, including this new one right here that I'm putting into the solution, is expressible as a linear combination of the basis. A basis is a spanning set. A basis is a spanning set. So we can write this vector V in terms of the basis. We can write V as, let's say, C1 times V1 plus C2 times V2 and plus dot 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 plus Cn times Vn. Now, so far I haven't mentioned the linear transformation at all. I'm simply saying we have a vector space that has a basis, and so any vector in that vector space should be expressible as a linear combination of the basis. This is an excellent question because it forces people to remember what is a basis. Of course, it's Li also, but in particular, it's also a spanning set. So every vector should be expressible this way. So then what happens when I transform that? T of V becomes T of, this whole quantity, C1, V1 plus C2, V2, and dot, dot, dot. And when you see something like this, T of this whole thing, what kind of knee-jerk reaction do you have? Does this get you thinking, oh, I know what I want to do with this expression? Say it again. Factor out the C's and also the plus signs. So guys, remember, what is a linear transformation? What are the properties? Properties of a linear transformation. T has to do two things primarily. Do you remember what I called them?
Respect.
Say it again. Respects addition and respects scalar multiplication. That's right, which means actually, guys, it respects linear combinations. Which is what I see inside these parentheses. This is a linear combination. So T will respect that. I can factor this thing out. C1 times T of V1 plus C2 times T of V2. Okay, so this is a key step where we're using the fact that T is linear. If it's linear, it's going to respect that linear combination. Oh, but we already know that T of V1 is 0. We already know that T of V2 is 0. They gave us that. That's part of the question. They gave us the fact that all of those are 0. So at the end of the day, what am I looking at? I'm looking at C1 times 0 plus C2 times 0 plus C3 times 0 and so on and so on. What's that all add up to? 0. That's it. That's the whole problem. So 2 very important things here to remind yourself about. First of all, that a basis is a spanning set, which means that every vector can be written in terms of that basis. That's one key idea from this blue part over here. The other key idea is that linear transformations respect these kinds of linear combinations. You can bust them apart. If you have a T in front of it, you can just do it piece by piece. Okay? So I know that was from chapter 6. We didn't really talk so much about that today, but I wanted to do at least one example using the properties of a linear transformation. Any questions here? All right, guys, I will be around a lot in the next 48 hours. Study well. I hope you get some rest along the way, though. Take care of yourselves, and I will see you on Thursday or in office hours. Have a great day.
Good night.
Bye.
Thank you.